Hello, and welcome to the PowerPoint for the acids and bases sections of our class. So you were assigned to go ahead and read the first three sections of Chapter 19. And a big part of those sections are to identify what acids and bases are and how they behave. So we're going to go over that here. So this is entitled Acids and Bases, as you can see. Okay, so first off, let's talk about the objectives for this PowerPoint. I figure if we knew what we were trying to get at, you'd have a better idea of what to look for. First bullet point here is to know the definitions of acids and bases. We're going to go over their definitions so we can tell, what they are, and we're also going to go over how we can identify them. Know the use of what's called the pH scale. You may have heard of it before, maybe you haven't. Some people even heard of it in different commercials for pH balanced hair, stuff like that. So pH scale is a scale that's out there and used for various things. The third bullet point says we need to identify an acid's conjugate base and a base's conjugate acid. In other words, what are these conjugate bases and conjugate acids? After we have a definition for acids and bases, we got to come up with a definition for conjugate base and conjugate acid. We also need to know what the reactions of acids with water are like. And they're all pretty much the same. So it's not that hard. It's just trying to figure out what the pattern is here. And the last one, know the difference between a weak acid and a strong acid. Acids are put into categories of weak acids and strong acids. Well, what's the difference between a weak acid and a strong acid? That's what we're looking at, okay? So let's get going. First off, the definitions of acids. And I have the two definitions of acids in chronological order here. And I say that because I'm going to talk about the definition of acid, the second definition first, then we'll go over the first definition, and we'll see how the first definition is pretty much, is the same, or at least it follows the second definition. Or these two definitions define the same thing. The first definition here is, the second definition here is what we call the Bronsted-Lowry definition of an acid. What is an acid? Well, these two scientists, chemists, came up with definitions of acids long time ago. And according to Bronsted and Lowry, these were two separate scientists who came up with this about the same time, so they both shared credit for coming up with it. The definition is that an acid is a hydrogen ion donor, or sometimes we call it a proton donor. First, let me just go ahead and remind you what a proton is, or a hydrogen ion is. Remember that a hydrogen is atomic number 1 on the periodic table. And what that means that it has a nucleus, and it has one neutron in the nucleus, and then it's got one electron that's out really in the 1s orbital. So in order to turn this into a hydrogen ion, we can go ahead and get rid of the electron. And if you get rid of the electron, all you basically have is a hydrogen ion. Remember that the hydrogen ion is positively charged, and I'm drawing here with my mouse here, so it's not all that great. The electron has a negative charge. And so if you just got rid of the electron, all you have is a positive proton, and that is your hydrogen ion. That would be your H+. All right, H because it's got one proton, and plus because that's the electrical charge on it. So what a acid is a hydrogen ion donor, and we can see kind of how that works. If we take an acid, here's an example of an acid, hydrochloric acid, HCl. And basically what happens with this when you put it in water is the HCl gives up the H+, and it separates the H+ from the Cl-. So these two become two separate species. And so as you can see, this chloride, basically you can think of it this way, gave up the hydrogen ion. And that's what makes it a hydrogen ion donor. Okay, so really you can tell when you have an acid because in the formula for the acid, the first element that you see in there is hydrogen. And we do that on purpose to kind of point out that, hey, this has got a hydrogen at the beginning, so therefore it is an acid. And that's hydrogen is going to be donated or has the potential to be donated. Sometimes they are donated easily, sometimes they are not. Okay, and so those are your hydrogen ions. Now, let's go back to this first definition over here. The first definition is what we call the Arrhenius definition. And this definition came in beforehand. And what this scientist Arrhenius, I think he was Greek, came up with is that an acid is a substance that produces hydrogen ions when added to water. Now, he basically, what he did is he noticed that when you put an acid into water, the hydrogen ion concentration started going up. And the more acid you put in, the more hydrogen ions were produced. So that's basically what he says. Well, the definition of an acid is something that when you put it in the water, it produces hydrogen ions. Now we know why. Later on, Bronsted-Lowry came up and said, hey, well, this thing gives off hydrogen ions. So that's why you have all these hydrogen ions in your water, because acid has hydrogen ions and it gives them away, right? So think of it as very donating, someone that wants to give stuff away. In this case, an acid is a substance that wants to give away their hydrogen ions. And I'll show you in a little bit how that plays out with all the acids. But first, let's talk about properties. So some properties of acids. When acids are added to an active metals, they produce hydrogen gas. What happens is here, when you have an acid, you got a hydrogen. These hydrogens will go ahead and sneak electrons from metals, causing the metals to corrode. So, a lot of times people have seen that an acid gets poured on a metal and it causes the metal to start bubbling and corrode. And you go, oh my God, if acids can do something to this metal, what could it do to me? The metals are hard, I'm not as hard. Well, it turns out that acids can do damage to us and our skin, but not in the same way as they do for metals. What happens with the metals is metals give away electrons real easily. So the hydrogen ions will go ahead and grab the electrons, and then they will pair up and they'll form H2. So you're producing hydrogen gas. Well, while those electrons are given off, now the metal becomes an ion and it starts to corrode. So that's why metals tend to corrode. Okay, and they form an ionic substance. Acids tend to taste sour. Most of your citrus fruits have acids in there. Acetic acid is actually the acid found in vinegar. I should say vinegar contains acetic acid. So when you taste vinegar, it tastes sour. Things like lime, lemons, oranges, pineapple juice, they all have a certain amount of citric acid in there. So they taste sour. So sour is a taste for most acids. You'll notice that in parentheses I have here, never taste a substance to find out what it is. If you know that an orange is acidic, you can taste it because you know that an orange is safe to eat, or a pineapple, or anything like that you already know. You can, oh yeah, it's sour, I see. But don't go, I don't know what this is. Let me taste it. It's just almost just makes sense, right? But we've actually had students go, hey, let me grab this and put it in my mouth and see what it is, and then had to be sent down to poison control. So you'd think that I really wouldn't have to say it, but I have it on my PowerPoint here because some people don't really use all their common sense, and I think it's important that I just tell people, if you don't know what something is, don't taste it. You can taste it once you know what it is and it's safe, but don't taste it if you don't know what it is. Okay, we don't test for acids by just throwing stuff in our mouth and go, oh, hey, that's sour. It must be an acid. There are other things that are sour too, but it's just not the way you do things. Third property, acids change the colors of indicators. Indicators, and I'll see if I can put up a video on it. Indicators are substances that change colors depending on whether something is an acid or a base. So we'll get into the definitions of bases in a little bit. We're really going to be focused on acids only because of the amount of time we've got left. But bases basically have the opposite properties of acids. So there is a substance called litmus, and we can put it on paper. And as you can see, the second sentence here says they also changed litmus paper red. So litmus is a substance that is red when it's an acid, and it's blue when it's in a base. So if you take some litmus paper, you can then go ahead and put an acid on there and it'll turn red. Okay, and as we'll see in a few slides, if you put a base on there, it'll turn blue. There are others. We have pH paper that has what's called a universal indicator. Not only changes colors, but it changes colors depending on how acidic something is. A thing called pH, which we'll talk about in just a little bit. Different pHs will give you a different color. All right, so some of the properties of acids and indicators that work with them. Actually, indicators themselves are weak acids that have different colors depending on the different levels of acidity that they are around. And the last one is that an acid, pH is less than 7. And once again, I've mentioned pH before for acids and bases. pH is a very big thing. We're going to talk about what pH is, not only here in this video, but I have another short video, talking about where we get this pH thing. But basically, acids have pHs less than 7. Turns out that 7 is a neutral pH. 7 is the pH of water and anything that is neutral. Anything below 7 is acidic. Anything above 7 is basic. And the smaller the pH, the more acidic it is. And once again, we'll talk about all those different levels of things in slides coming up. Okay, but those are some of the basic properties of acids. React with metals to produce hydrogen gas. They also dissolve the metals. By doing that, they turn the metals from neutral atoms to ions. Acids taste sour. They change colors of indicators, and they have pHs less than 7. So this slide right here, I guess it would have been better if I put it before the properties, but it's all right. It's here. We said that acids are hydrogen ion donors. Acids donate their hydrogens by dissociating from them. In other words, separating from them. So here I have a list of 6 different acids. The first one here is hydrochloric acid. The second one is nitric acid. The third one is acetic acid. The fourth one is sulfuric acid. The fifth one is hypochlorous acid. And the sixth one is hydrocyanic acid. We actually went over how to name these first semester. I don't know if you remember at this point in time, but there was a naming convention depending on how basically what an acid is an anion, a negative ion with enough hydrogens on it to form a neutral compound. And whether that anion ends in IDE, ide, or ATE, ate, or ITE, ite, whether the anion ends in those names, you would name the acid accordingly. Right? I'm not going to go into that again. That's something from chapter 10. We did that back in chapter 10. But here, what I want to do is show these guys dissociating. So here, they've got a whole, they're neutral, right? And you'll notice that the first letter in each of these is an H. You'll notice that the third substance here, acetic acid, has hydrogen at the front and then 3 hydrogens somewhere here in the middle. Why did I do that? Why didn't I just put H4C2O2? Or why didn't I just go ahead and put C2H4O2? If I did that, then, this is the big giveaway that it's an acid. We put a hydrogen in front. It turns out that not all hydrogens are acidic, depending on how they're held together. If I were to go ahead and do the Lewis structure for this acetic acid right here, once again, remember, this is acetic acid, and acetic acid is found in vinegar. Right? And its structure looks like this. We've got a carbon attached to the 3 hydrogens later. Right? I know this is not the best drawing, of my Lewis structures that I've ever done. Well, some people might not say it's not too far off of what I normally do. So we got a carbon with 3 hydrogens on it. Then there's another carbon, and that carbon has a double bonded oxygen in it, and then a single bonded oxygen and the hydrogen. All right. So this hydrogen right here is your acidic hydrogen. It is this one over here. Okay, these other 3 hydrogens here are not acidic. Why? Because they're attached to the carbon, and the carbon really holds those hydrogens really tight. It's really hard to get the hydrogen off of this carbon. So we say that these are not acidic. Now, nothing is completely non-acidic, but it's very hard to take these hydrogens off the carbon. Right? If you ever take organic chemistry, you'll see why. We're not going to go into all the explanation of that here. This hydrogen, on the other hand, is held relatively loosely. And by relatively loosely, I mean it's held on pretty tight, but it can be pried away, not too hard. And the reason for that is because of this, we call this a carboxyl group here. A carboxyl group has some resonance to it. So we got the carbon-oxygen double bond, and then we got the carbon-oxygen single bond that's attaching to the hydrogen over here, right? And if you recall way back in the day, when we talked about Lewis structures, we put these little dots on here to represent lone pair of electrons. So if we take the hydrogen off, then this pair of electrons right here just becomes another pair of electrons here, and this whole structure right here becomes a negative charge. Okay, and when you see this structure right here, you can actually draw another equivalent structure. Remember we called it a resonance structure, went over it kind of quickly. But if I move these electrons so that this pair of electrons forms a double bond, and now that this forms a double bond here, there's going to be 5 bonds to this carbon. Not a good thing. So one of these pair of electrons then can go ahead and jump back out to this other oxygen, and it forms a structure that looks like this. And so we can put a single bond to the oxygen on top, right? And now we have the double bond to the oxygen on the right. This is basically the same structure. Here I have the negative charge on this oxygen here. Here I have the negative charge on this oxygen here. But in both cases, the oxygen's a negative charge. Because we can delocalize the electrons here, in other words, we can have the electrons move around and still give us valid Lewis structures for them, then this structure, and these are actually 2 structures. Here's 1 and here's 2. This structure right here, all put together, is actually relatively stable. And so it doesn't kind of fly apart. It doesn't say, hey, hydrogen, I need you. It says, basically, we like you. We'd like you to stay. But if you need to go, okay, we'll manage. And so that's what happens when you lose a hydrogen. And that's, once again, what does an acid do? Acids lose hydrogens, hydrogen ions. So therefore, this lone pair of electrons stuck around here. And how strong an acid is, as we're going to see later on, depends on what kind of structure is left after you got rid of the hydrogen. Get rid of this hydrogen and you have a bad structure. There's a negative charge on carbon, which is not a happy thing. Right? So carbons are not happy when they have negative charges on them. On the other hand, oxygens, not happy campers, but yeah, they're like, whatever, I'll take a negative charge on it. Oxygen is more electronegative than carbon by 0.5 points. We talked about electronegativity earlier also. So it can handle the negative charge much better than the carbon can. So that's why the hydrogen can be pulled off or given away much more easily. That's what makes it an acid. Okay. The point here was that sometimes we will write hydrogens in 2 separate places. And that's because some of the hydrogens are acidic and some are not. And so we put the acidic hydrogens on the front and we put the non-acidic ones later on. Okay. So let me go ahead and get rid of all this because that's not what I want to show with this slide. On this slide, what I want to show is that Acids are hydrogen donors. And as you can see right here, what we're going to have is the anion move away from the hydrogen ion, and the hydrogen ion separates from the rest of the molecule. That's what an acid does. The rest of the molecule gives up its hydrogen, moves away from it, or I guess you can say it kicks the hydrogen off. And what we're left with, as we're going to see later on, is the conjugate base of each of these acids. So we start off with the hydrogens, those are the acids, and then the substance, the hydrogen separates from the rest, excuse me, of the molecule and leaves the conjugate base of it. One thing to note, you'll notice that the fourth acid here, H2SO4, sulfuric acid, is the only one that has H2 in the front. That's because it has two acidic hydrogens, right? As opposed to acetic acid that only had one acidic hydrogen and the other three hydrogens were not acidic. Sulfuric acid has two acidic hydrogens, and so when it dissociates, it will lose both of them. Well, it's a little more complicated than that, but we won't get into that because that gets a little complex. So, but that's what an acid does, okay? So there's 6 acids giving up their hydrogens, donating their hydrogens, and that's what they do. And once again, those hydrogens then can go ahead and do all kinds of stuff. They can land on other molecules, they can land on metals, they can corrode, that'll corrode stuff, they can land on other substances in your cells that will go ahead and will change how they behave, because now they will go from a neutral substance to a protonated substance, a positively charged substance, and that changes the properties, even the properties of whether they can go through membranes or not, because now as positively charged, they become as they're positively charged, they become hydrophilic or polar, right? All right, so that's what an acid does. Now let's take a look at bases, and I'm going to blow through bases because they're just the opposite of acids. Once again, I'm going to start with the Bronsted-Lowry definition because I think it's the one that a little makes more sense. A Bronsted-Lowry base is a hydrogen ion acceptor. Anything that will grab a hydrogen ion is a Bronsted-Lowry base. So all these things that we saw earlier here, they are bases because they grabbed a hydrogen at some point in time. And some of these still can grab a hydrogen. It gets complicated as to whether they would or not, right? They just give up a hydrogen. Why would they grab some? Well, some do, some don't. But the fact that they could have started with that makes them hydrogen ion or proton acceptors. Okay, so that's the Bronsted-Lowry definition. The Arrhenius definition is that a base is a substance that produces hydroxide ion when added to water. So here's your hydroxide ion. And so how does this work? If something is a hydrogen ion acceptor, why would it produce hydroxide ion? Well, because when you add it to water, well, water is H2O, right? So let me go ahead and write that out, H2O here. Actually, you know what I'm going to do? I'm going to get rid of that. And go back over here. And I'm going to write it not as H2O, but HOH. This is H2O, right, with as a structural formula. So if something wants to grab a hydrogen, it can grab it off of a water molecule. And let's say it grabs it off of the water molecule. And what you end up with, after you've lost that hydrogen right there, is you end up with an OH. And since it was a hydrogen ion acceptor, then this lone pair of electrons, this pair of electrons that was a bonding pair here, ends up staying on the oxygen and ends up being a pair of electrons. There should have been 2 others up here, right? And I'll just go ahead and put those on here. This forms our hydroxide ion that we learned about way back in the day, once again, okay? So by grabbing hydrogens off of water, you produce hydroxide ions. Right? Arrhenius, like I said, kind of got some water, said, hey, I put this stuff in the water and it formed hydroxide ions. I didn't even know it had hydroxide in it. Well, it turns out that whatever the base was, let's say it was a base like cyanide. Cyanide is a base. The cyanide picks up the hydrogen here, and by adding the cyanide in the water, it picks up this hydrogen and creates the hydroxide that we see right here. Okay, so those are your definitions of bases. Properties of bases. Similar, not completely the opposite, but similar to acids. When active metals are placed in water, they form bases and hydrogen gas. We actually saw some of this stuff happening, although we didn't really go into a lot of detail when we saw videos of chemical reactions. We saw a video where we put metals in water and it fizzed around. Next thing you know, it caught fire, exploded. There was even one where somebody threw a chunk of, I think it was potassium or sodium, into a lake, and it started bubbling, and the next thing you know, it caused an explosion. That was the hydrogen gas that created the explosion, because it was heat was also being generated. So these active metals like potassium and sodium and cesium and all the group 1 metals, they do this. Lithium also does this. And they form a hydroxide. So if you put in potassium, you get potassium hydroxide out of it. You do sodium, you get sodium hydroxide and hydrogen gas. Okay. Bases taste bitter. So people is a good example of a base. And if you've ever had soap in your mouth or taken a bite of soap, I don't know why you would, but I guess some people used to be disciplined that way, or take a bite of soap. But bases taste bitter. And once again, the disclaimer, never taste the substance to find out what it is. Bases change the color of indicators. We already talked about this. Acids change one color, bases change it another. And the pH of bases is greater than 7. Okay. So that's what acids and bases are. Now let's talk about this pH scale a little bit. This pH scale is a scale just to show how acidic or basic something is. Turns out that things that are neutral have a pH of 7. And in my next video, I'll go into much more detail as to why 7 is a neutral pH. But right now, I'm just going to tell you, if something is neutral, it has a pH of 7, or something has a pH of 7, it is neutral. Water, pretty much anything that's not an acid or a base. Methane, carbon, I don't want to say carbon dioxide, but sugar, everything that's not a base has a pH of 7. Acids have a pH of less than 7, right? And the smaller the number, the more acidic. Bases have a pH greater than 7, and the larger the number, the more basic. Okay. Here's some examples of things that are acids and bases and where they are on the pH scale. One thing to point out, and once again, I will talk about this in much more detail on the next video, is that the pH scale has got these numbers, right? But these numbers represent, they don't represent like actual numbers. They represent powers of 10. They represent exponents. So every number represents a number that is 10 times larger than the one to the right. So every number to the left represents a hydrogen concentration 10 times larger than the concentration of hydrogen ions to the right. So 6 is 10 times more acidic than 7. 5 is 10 times more acidic than 6. 4 is 10 times more acidic than 5. 3 is 10 times more acidic than 4, etc., and so on. And obviously, if 3 is 10 times more acidic than 4, 4 is 10 times more acidic than 5, that means that 3 is 100 times, 10 times 10, 100 times more acidic than 5, and it's 1,000 times more acidic than 6. So 3 and 6. 3 is 1,000 times more acidic than 6. Right? They're all powers of, they're all numbers that show the powers of 10. And I'll show in the next video how that works out. And here I just want to kind of show things. So let's start off with pure water here, right in here in the middle. Milk is a little slightly, there's a little bit of lactic acid in there. Tap water's got all these other stuff in there. So tap water is about 6. Unpolluted rain actually has a pH of less than 6, in the 5s. And the reason for that is because up in the atmosphere, there is carbon dioxide, plenty of carbon dioxide. When the carbon dioxide combines with the water, it forms carbonic acid. So there is some carbonic acid that is in the water, and it's not considered acid rain. Acid rain also has some nitric acid to it and sulfuric acid to it because there's so much nitrates and sulfates in the atmosphere that when the water combines with them, now you end up with all these other acids that are formed. Coffee about pH of 5, beer 4.5, tomato juice 4, soda water 3.5. There's a bunch of carbon dioxide there, so same way that unpolluted rain gets acidic, but the soda water has more carbon dioxide, and the carbon dioxide combines with water, forms carbonic acid. Orange juice about 3, vinegar less than 3, about 2.7, lemon juice way down here. Stomach acid 1.5, and your stomach creates hydrochloric acid, and it does so that it's supposed to be acidic. It does so that it kills bacteria when it gets in there, so it doesn't get into your system. Also, it helps kind of soften the food as it's getting ready to digest. It helps some of the enzymes that start breaking down proteins in the meat, helps them get going. So you start getting some acid in there and starts working. So those are examples of acids. A lot of these you find at home. Human blood is a pH of 7.4. I have a whole thing on the pH of human blood, and it turns out that human blood has to be 7.4. It cannot be any higher, it cannot be any lower. If your pH, your blood is off by 0.1, you die. So your body takes a lot of trouble to keep the pH just at a certain time, because if pHs change, so do the molecules within your blood, and we can't have that because things won't work. And I bring this up because one of the things I always rant about is I go to the grocery store and I see these pH waters, or the alkaline waters. The word alkaline means basic, right? So everything above 7 is basic. Another word for basic is alkaline. Actually, that's kind of an old word. Base, alkaline. Bases are much more modern term. Sorry, that's supposed to be an A, and so is this one. So there's this alkaline water in the stores, and it's got a pH of 9 something. I've heard people say, oh, well, you have to control your pH because your body, if it's too acidic, it's just not going to function correctly. And I, to a point, that's true, but you have very little control over what your body's pH is. Your blood in itself self-controls it. And it does so by releasing or taking in more things like bicarbonate ion, which is part of baking soda, with the conjugate base of baking soda. That's here at 8.1. Also, there's phosphates in there. Carbon dioxide gets together with the water and carbon dioxide. You know that you give off carbon dioxide, your cells give off carbon dioxide, then they get taken out of your respiration. So your body will actually already handle this by causing you to breathe faster or slower, to either release more carbon dioxide if your acid is getting too acidic, your pH is getting too low, or it'll have you breathe a little more slowly to keep more carbon dioxide in if your pH is getting too high. So there's all kinds of stuff your body does. And so if you drink this alkaline water, and I guess it doesn't hurt anybody, but it costs like 4 times more than regular water. And if you buy it, it's not going to do anything. Why? Because it's a pH of 9 something. Your stomach acid is 1.5. So if you consider that 9 is about 2 digits over from 7, and 1 is 6 digits over from 7. We always said every number here is a power of 10. That means that your stomach acid is about 7. Let's see, goes to 2, 5.5. 5.5. That's 10 to the 500,000 times more acidic than water. On the other hand, this alkaline water is only 100 times more basic than water. So really, if you calculate it out, your stomach acid in your stomach is going to be 550, like 5,000 times more acidic than this water. And we're not going to get into the neutralization section. Basically, the alkaline water is just going to be sucked up by all the acid. Does nothing. And even if it did something, your body actually goes, ooh, the stomach is not acidic enough. Let's make more acid. Now, sometimes it makes too much acid, and you take acids, which are bases, and you do that just so that you don't have too much acid coming up into your esophagus. Yeah, there's all pH goes a lot into the physiology. Hopefully, I didn't go too far off track, but I think these are kind of important things to know. Why am I learning about pH? Well, because people are selling things to you at 300% markup that really don't do anything. So I'm just kind of letting you know. Anyway, so let's talk about these things. Baking soda, a little bit over 8. Baking soda is sodium bicarbonate, and it's the conjugate base of carbonic acid. So the sodium bicarbonate, the sodium does nothing. It's just a bicarbonate ion, and let's see, it's HCO3 minus. That's the base. And put another hydrogen on it and cancel out the negative charge, and it becomes carbonic acid. We'll see that in just a little bit. But here, baking soda, just a little slightly. Bleach, Clorox is like about pH of 11. That's pretty basic. Same with ammonia. People use ammonia cleaners. It's about pH of 11. Photo developer, you guys don't use it anymore because we don't develop photos anymore. pH of 12. Lye right here is actually sodium hydroxide, NaOH. And sodium hydroxide is a very strong base. Actually, I contend that hydroxide is the only strong base, at least that we see in a class like this. Everything else is considered a weak base, but that's a whole other thing. So its general name is lye, but it's sodium hydroxide. Potassium hydroxide, anything that has hydroxide is lye and has a pH of 14. It's as basic as stomach acid is acidic, right? But you want to be careful. They put this stuff in like drain opener and stuff like that. So you get that stuff in your eye and you can cause blindness on both sides of the spectrum. A lot of acid can cause blindness. A lot of base can cause blindness. When we do stuff in the lab, this part of the school year, we're not going to be able to this year, but as part of the school year, always use goggles. Okay. All right. So that's the pH scale. Reactants of acids and bases. This next one is just what happens when you put an acid or a base in water? Well, actually, we're going to stick with, I think, acids. We won't go to bases. But before we do, we need to define what a conjugate base and a conjugate acid are. And we've already kind of talked about it a little bit, but basically, let me give you the definition. The conjugate base of an acid, every acid has a conjugate base, by the way, and every base has a conjugate acid. And they are conjugate bases of specific acids because the conjugate base is the base formed by removing an H plus from an acid. So if I started with HCl and I removed an H plus from HCl, I get Cl minus. So Cl minus is the conjugate base of HCl. If I start with HNO3, nitric acid, and I get rid of the H, what am I left with? NO3, nitrate. So therefore, NO3 minus is the conjugate base of HNO3. Can you see that? It's the acid without the hydrogen in front of it. And chloride is specifically the conjugate base of HCl. Chloride is not the conjugate base, nor will it ever be, of HNO3 because HNO3 has no chlorine in it, and vice versa. Sometimes some of our acids can be positively charged, like ammonium here. NH4 plus is ammonium. If we get rid of a hydrogen, and with the nitrogen acids, we don't put the hydrogen in front. I don't know why, but to tell you that it's an acid, but this is an acid. If you get rid of one of the hydrogens there, and the plus, you get NH3. This is the conjugate base of NH4 plus. So see the difference between the acids and their conjugate bases? It's just get rid of a hydrogen. The conjugate acid is the acid formed by adding a hydrogen to a base. All right, so this is the acid we're going to form when a base does what it does, which is pick up a hydrogen ion, right? Remember that acids are hydrogen ion donors, so you get the conjugate base when an acid does what an acid does, which is remove a hydrogen ion from itself. Well, you get a conjugate acid when a base does what a base does, which is add a hydrogen ion to it. Right? So if you start off with, this is an acetate ion. If an acetate ion picks up a hydrogen, it forms acetic acid. Cyanide ion also is a base, and if it picks up a hydrogen from water or from somewhere else, it forms HCN, hydrogen cyanide. Okay, so really, all a conjugate base is an acid without the hydrogen on it. All a conjugate acid is a base all a conjugate acid is the acid that was formed by taking a base and putting a hydrogen on it, and plus charge also. Which brings us to, how do acids and bases react? I'm not going to worry about this up here part, but basically, an acid and a base react. Well, I guess we will go over it. Acid and a base reacts to form the conjugate base of the acid, so the conjugate base of this acid, and the conjugate acid of this base. So HCl, basically what they're doing is just, we call it proton transfer. They're just swapping hydrogens. So HCl reacts with cyanide. The H here goes onto the cyanide, forming HCN. And then this HCl, without the hydrogen now, what's left with is chloride. Same thing here. Here you've got your acid, HCl, reacts with acetate. So acetate's the base, and the base goes ahead and grabs the hydrogen, forming your acetic acid over here. And once again, once you take a hydrogen off of HCl, you're just left with Cl minus. You can think of water as being an acid and sometimes a base. It's neutral. Sometimes it's an acid, sometimes it's a base. So acids always react the same way with water. If I go ahead and I'm going to represent just any old acid as HA. And why do I use HA? A for the acid, and the acids always have a hydrogen. That's why I put the H in the front. So just so you know what I'm doing over here. Also, there is this substance called hydronium. Its formula is H3O+. It's called hydronium. And basically what hydronium is, it's a hydrogen ion piggybacked onto a water molecule. It's H2O, but then the hydrogen ions can't exist just by themselves. They don't like it. So what they do when they're in water solution, there's water everywhere. The hydrogen ion, instead of just floating around by itself, will just jump onto a water molecule and form hydronium. So sometimes we'll see it written as H3O+, sometimes it's just H+. This is a hydrogen ion, this hydronium, they behave the same way. Okay. So down here at the bottom here, I have 4 reactions of acids with water. The first one is a general acid formula, and the other are specific ones. But basically, the way this works is your acid right here, this is your acid, reacts with water when you put it with water, reacts with water right here to form hydronium. Right, there's your hydronium. And this A- represents the conjugate base. So basically what happened is this hydrogens fell off of that conjugate base, went onto the H2O, forming H3O+, and the conjugate base. And that's the general formula, what happens when an acid is put into water. All right. HCl and water, the H jumps onto the water, forms H3O+, right? H2O, add another hydrogen on it, forms H3O+. And then what's left after the hydrogen, the HCl lost the hydrogen, just the chloride. HNO3, hydrogen jumps onto the water, forms a hydronium again. And what's left of HNO3 without the hydrogen is NO3 minus, the conjugate base. This is the conjugate base of Cl minus HCl. This is the conjugate base of HNO3, sorry. The last one, acetic acid, the hydrogen jumps on the water, forms hydronium again, and leaves the conjugate base. This is just acetic acid here without the hydrogen on it. Notice the pattern. It's always the acid here. These are all your acids. React with water and forms hydronium. And these are all the conjugate bases of these acids over here. Okay, so that's how it works. Now, so we don't have to write that all the time. We can cancel stuff out. Instead of having to write that the acid reacts with water to form hydronium and the conjugate base, we can just go ahead and cancel water out on both sides. If you cancel water out, if you think of hydronium, once again, as H2O with a hydrogen ion piggybacked onto it, if you go ahead and think of hydrogen as that, and so cancel this water out with a water over here, then what you're left with is just an H plus, which I will write right here. And that leaves you with HA breaks up into H plus A minus. Right? So basically just this thing is broken up. The H separates from the rest of the molecule, forms H plus and the conjugate base. And we see it down here. HCl, what's really happening is HCl reacts with water, hydrogen jumps on the water molecule forming hydronium and chloride. But we can write it as the H separates from the chloride forming H plus and Cl minus. Same thing, okay. All right, so let's get to the last part here. The acid constant and strong and weak acids. Okay. So I told you there was two categories of acids, strong and weak acid. What's the difference? And how can we tell whether something is a strong acid or whether something is a weak acid? Well, first off, whether something is a strong acid or a weak acid really depends on the equilibrium constant for that reaction. See all these reactions that we had over here? They have equilibrium constants. And so whatever the equilibrium constant is going to tell you whether that reaction occurs to a great extent or a smaller extent. You'll recall when equilibrium constants are large, that means you're going to make more products than reactants. And when equilibrium constants are small, much less than 1, then you're going to end up at equilibrium with only a small amount of products and mostly reactants. So if you look at, for example, oops, this is liquid. This reaction here. Hydrogen cyanide reacts with water, which is a liquid, to form H3O plus and Cn minus. Everything else is aqueous. You'll recall when something is aqueous, we don't need to put it in the law of mass action, right, or the equilibrium expression. So for this reaction, our equilibrium constant is H3O plus times Cn minus goes to form, divided by HCN gives us our equilibrium constant. We call this constant Ka, and the A stands for acid. It's an acid constant. And so this equilibrium constant is going to tell us at equilibrium what we have more of, the products or the reactants. If at equilibrium the products, if there's much more products than reactants, then our Ka is going to be greater than 1. If at equilibrium there's only a small amount of products and mostly reactants, more reactants than products, then our Ka is going to be less than 1. Okay. And by the way, down here at the bottom, if we just went ahead and made the Ka for the reaction with the shortcut that we have down here, as opposed to the whole thing, it kind of looks like this, right? Instead of H3O plus, H plus. But then we already said that H plus is the same thing, and we'll put it as a concentration. H plus is the same as H3O plus, really. Because really what H plus is a bunch of, oops, I got to focus on that. Really what H3O plus is this H plus piggybacked on a water molecule. So either way, these two values would be the same. All right, one way or the other. So acid strength. What's a strong acid? Well, the larger the Ka, the stronger your acid, because you're going to get more products once we hit equilibrium. These acids dissociate. The word is dissociate. When we see something like this occurring, we call this dissociation, right? And you can see how it's dissociating. The H and the Cl are separating from each other, so it's dissociating. So the extent to which these things dissociate really depends on the equilibrium constant. So the larger the Ka, the stronger the acid, because the more dissociation is happening. And the more dissociation is happening, the more H plus we're getting. And that's, once again, those are the buggers that go around doing all the dirty work. Right? So strong acids are acids with Ka that are greater than 1. Usually they're much greater than 1. Here's the nice thing. For our purposes, strong acids are going to assume that that these acids are going to completely dissociate. All the molecules break apart, 100% of them. Weak acids are acids with Ka that are less than 1. And basically, the smaller the Ka, the weaker the acid. It's not just whether an acid is strong or weak. We can break them up into 2 general categories, strong acids and weak acids. But within the weak acids, there are ones that are weaker than others. There are some that are stronger than others, right? So this thing says the larger the Ka, the relatively stronger the acid is. And basically what happens here is in a weak acid, only a small percentage of weak acid molecules dissociate, typically about 5% or less. We don't have the time to go into how I would calculate that out. There's definitely a way of calculating out. I could do it. You could do it if we had another week of school, but we don't have that. But just to show you what happens, the difference between strong and weak acids. So when a strong acid has a Ka greater than 1, if we did all the calculations, basically you'd start off with when you just had the acid before you put it in water, all the molecules would be neutral acid molecules. Once you put it in water, though, all those break apart and turn into hydrogen ion and the conjugate base. So at the end, once the equilibrium is established, and I put equilibrium in air quotes at this point in time, all your acid molecules have been turned into H plus molecules and conjugate base molecules. So the acid is completely dissociated. If you had, a million acid molecules, they would turn into a million H plus ions and a million conjugate base ions. Okay, that's what happens in strong acids. So, and the key is how acidic is something, how much hydrogen ion is in here. So this is the key, how acidic something is. And we're going to see in the next video, I promise you, it's much shorter than this one, that the concentration of H plus is what determines your pH. So the more H plus, the lower the pH. And the less H plus, the higher the pH. Go into that in the next video. In a weak acid, as I told you, small percentage of the acid molecules break up. So here we're starting off with 100% of our acid molecules are around. If I were to have a bottle of acetic acid, all the molecules in the acetic acid, the pure acetic acid, look like this. Once I put it in water, it starts reacting with the water. And once I put, let's say I had a liter of water and I put in 100 milliliters of acetic acid. Some of the acid molecules, this part right here, right, this part right here, that at the top here, they would turn into H plus and A minus. They would be the ones that went ahead and dissociated. But most of them don't. And remember, this is an equilibrium. It's not like these guys associate and that's it. Some of these get together and go ahead and turn back into these guys. But some of these then continue dissociating. And there's kind of a cycle going on here. Okay. So something like acetic acid found in vinegar, citric acid found in your citrus fruits like lime. What they're doing is they're putting out a certain amount of hydrogen ion, putting a certain amount of acidity out there, dropping the pH to a certain level. But then they're also going backwards. So some of these guys that had like the H plus and the A minus were created by the HA breaking apart. Well, now they're going to get back together and then turn back into an HA. Right? And so because equilibrium constant is small, that means that equilibrium, you get very little H plus and A minus. Okay. That's what makes a weak acid. So here is a whole list of strong acids, weak acids. If you want to look at them in much more detail, you can. Just click pause on the video. I'm not going to spend too much time on this, but these are the names of all these acids. These are their formulas. You'll notice they all have hydrogens. As I told you, have hydrogens in the front, right? And they have different Kas. And some are the Kas, all these, because they're weak acids, have Kas that are smaller than 1, right? Which means that their exponents are negative exponents. Some can go as high as, let's see, in this thing I have this one right here, oxalic acid and hydrogen sulfate ion. These guys are 10 to the minus 2. Those are the strongest acids in this group. Still less than 1, but strongest. And some of these other ones are like, look over here, boric acid. It's got a pH way down at 1.6 times 10 to the minus 4. So very low Ka, very weak acid. It's not real. Basically, what it's saying is this HbO3, already 2 negative charges, does not really want to give up that hydrogen too easily. H2BO3 has a slightly higher, not much, but slightly higher Ka. So this one is willing to give up one of these hydrogens more than this one is willing to give up its hydrogen. That's basically the way it goes. Now, there's a whole list. This is just a partial list of weak acids. There's like hundreds of weak acids out there, and you can calculate, you can get their Kas. You can actually use Kas in calculations to figure out what the pH would be. And don't even worry about the pKa. This is a whole nother ball of wax here. What about strong acids? We have a list of strong acids. There's 6 of them, right? And we said that we're going to assume that they're all completely, they dissociate completely. So, this is HCl, hydrochloric acid, hydrobromic acid, hydroiodic acid. I like to think of this as the hydrohalogen acids. Cl, Br, and I are in the same column 17 on the periodic table. So you put a hydrogen on them, they're a strong acid. Right? And then there's these other 3. Sulfuric acid, H2SO4, perchloric acid, and nitric acid. These guys can be pretty nasty acids. All right, that's the end of this video. Hopefully didn't go too long, but just want to give you guys some definitions. We definitely didn't get into all the problems. I can go 2-3 weeks on this chapter, but we've just got a few days. I just want you to get some idea of what acids and bases are, and what some of the definitions of the things of acid-base vocabulary is. Okay, so hope this helped. Check out the next video on what is pH. Like I said, I'll show you how we get the pH and how we decide pH 7 is neutral, and how there's a logical thing about it. All right.